Welcome to this explainer. Whenever I look at a massive piece of infrastructure, say a sprawling railway network or a huge power grid, I always catch myself wondering, how on earth do we keep this from just descending into total chaos? I mean, with millions of moving parts and endless lines of code, how do you actually guarantee the final product is fundamentally safe? Well, today we're putting on our systems engineering hats to explore the hidden architecture of safety. We're going to look at the governance, the stage gates, and the audits that invisibly protect us every single day. Okay, let's dive right into this. Here is our syllabus for today. First, we'll cover the fundamental need for governance. Second, we'll enter the stage gates. Third, we'll look at the purpose of decision gates. Fourth, capturing technical risks. And finally, the role of audits. Section 1, the need for governance, why intuition fails. So when we're building simple things, common sense usually keeps us out of trouble, right? But as we scale up to these massive complex systems, our human brains kind of hit a wall. Intuition rarely predicts the behavior of novel, complex systems. You might design individual elements to be perfectly safe, like a relay that physically cannot stuck, or a cable that defaults to a safe state if it snaps. But when you wire thousands of those together with software and unpredictable human operators, the system often converges on a solution that absolutely no one originally anticipated. Without a rigid, structured process of governance, different engineering disciplines just become isolated in their own little silos, and a massive project can very easily lose its way. Now, what's really interesting here is that we have to draw a hard line between two concepts that get constantly confused. Quality management ensures the system does what was intended. It meets the specs. Safety management, on the other hand, ensures that what was intended was actually safe. You can build a perfectly high-quality bridge that does exactly what it was engineered to do, but it is fundamentally unsafe if it's built right over an active volcano. Safety management is a completely different lens, heavily focused on identifying hazards and assessing those really improbable risks. Let's move on to Section 2. Enter the stage gate, the core mechanism. Look, if a project takes years to complete, we literally cannot wait until the very end to figure out if it is safe. We need a stage gate. That's a discrete step in a project where progress is checked against requirements. Think of it like a giant cross-country road trip. You don't just put on a blindfold, hit the gas, and hope you end up in the right state. You stop at specific waypoints, you check your map, you check your fuel, you make sure all your passengers are still in the car. Stage gates are those exact waypoints for complex projects. They force everyone to stop and check that the project is delivering what's expected, keeping teams from just running off in their own directions. And this whole philosophy operates as a beautifully simple, closed-loop feedback control system. Notice the plan, do, check, and act cycle. Stage gates fit perfectly right into this checking and reviewing phase. The information flows down through planning and implementing, sure, but the auditing and reviewing loop right back up to keep the whole system stable. It's this continuous loop of verification that literally underpins everything we do to keep massive infrastructure from failing. All right, Section 3, purpose of decision gates, the checkpoints. So, what exactly are we looking for when we pull the emergency brake and stop a project at one of these stage gates? Well, we are performing essential gate checks. First, we confirm that evolving designs actually comply with the latest legislation and safety standards. Second, we verify objective, documented evidence that requirements are being met. We absolutely cannot just take a team's word for it. And third, and this is a big one, we make sure we remain aligned with the original customer problem. It is startlingly easy for a brilliant engineering team to get totally carried away solving a really fascinating subproblem, only to realize years later it wasn't the problem the client actually paid them to solve. We actually call this issue alignment and drift. It's like a giant puzzle where the pieces started changing shape halfway through. Gates force a pause to ensure the project doesn't just offer something, different, that the client never even asked for. An isolated software team might develop a truly magnificent new feature, but if it doesn't integrate safely with the physical hardware, or if it strays from the core safety requirements, it's completely useless. Governance, applied through these stage gates, actively reels the project back in and forces everyone to look at the big picture together. Which brings us to Section 4, capturing technical risks, the defense. So the crucial point is that beyond just keeping the project on track, stage gates serve as our primary defense mechanism for handling tangible threats. This is where the real safety engineering happens. We absolutely must adequately capture the technical risks, log them, and then assign each one to a specific named owner. Accountability is literally everything here. Finally, we mitigate.
Whether that means adding a redundant backup system or just simplifying the design altogether, that risk must be neutralized or reduced to an acceptable level before the project is allowed to proceed to the next phase. But here is the catch, and it's a critical one. Independence is key. The verifiers and assessors must be independent to avoid shared misconceptions. Think about it. If I build something, I might have a total blind spot to its flaws. If my own team reviews my work, we might all suffer from the exact same groupthink. True governance requires an impartial set of eyes, completely shielded from peer pressure or the commercial pressures of rushing a product to market.
And finally, Section 5, the role of audits. Verification.
We've talked a ton about checking the product and the design at these gates. But how do we check the checkers? It prompts a pretty profound question for any engineer or manager out there. How do we objectively prove the process we used to build the system was actually safe? How do you prove to a regulatory body that you didn't just, get lucky? Well, the answer lies in safety audits. A safety audit isn't just asking, does the light turn green when it should? It is rigorously checking the underlying work against known, published benchmarks and standards to ensure the strict rules of engineering were actually followed. It is digging deep into the documentation and the traceability. It's the ultimate benchmark test to ensure the safety functions and requirements were structurally met throughout the entire lifecycle of the project. This audit verification really happens in 3 distinct steps. Step 1, you clearly define the system's safety requirements. Step 2, you establish a published standard as your known benchmark. And Step 3, you audit the entire process to ensure compliance. This becomes your hard, auditable paper trail. It proves the stage gates functioned correctly, that independence was actually maintained, and that risks were genuinely mitigated, not just swept under the rug.
Which brings us to this incredibly powerful realization. Good systems do not just happen, they are designed and planned. When a complex system operates flawlessly, it looks effortless, right? It almost looks like magic. But behind that flawless operation is an unyielding, rigorous architecture of governance. So I want to leave you with this final thought. The next time you board a high-speed train or rely on a massive, complex network to get you home safely, ask yourself, what invisible gates did this system have to pass through? And what hidden audits were performed to earn your trust today? Thank you so much for joining me on this explainer, and keep questioning the complex world around you.